All right. Welcome to another deep dive. You ready to go deep?
Mm.
Today, we're taking a look at kernels and memory.
Ooh, fun.
You sent in a pretty interesting mix. Looks like some technical documents and study guides.
Right.
And so seems like you're really looking for a clear but thorough understanding of this interaction between the two.
Definitely.
So to kick things off, maybe you can help us understand what a kernel is. Is it like a physical piece of the computer, like a chip or something?
It's actually not. The kernel is software, and it acts like a bridge between the hardware and the applications that you use every day.
So it's kind of like the go-between.
Exactly.
What does that actually look like in practice? What does it actually do?
So think of it this way. When you want to listen to music or edit a photo, even just browse the web, all of these actions require the software to interact with the hardware, the
Hmm.
processor, memory, and storage. The kernel is making that happen. It manages and allocates these resources and ensures that everything runs smoothly.
So it's kind of like a conductor,
Yeah.
making sure all the parts work together.
And one of the most critical roles that it plays is managing the computer's memory.
Okay, so when we talk about memory in this context, we're
Yeah.
talking about RAM, right?
Yes, primarily. RAM stands for random access memory.
Okay.
It's like the computer's short-term memory, where the data and instructions for currently running programs are stored. It's
Yeah.
really fast, which allows the processor to access information almost instantaneously.
Wow. So the kernel's in charge of this super valuable real estate.
Absolutely. It decides which program gets how much RAM, ensures that no one program is hogging resources, and prevents programs from interfering with each other,
Okay.
assigning designated memory spaces, kind of like an air traffic controller.
Wow.
It's directing the flow of data in and out of memory.
That sounds really complex. How does it keep track of everything?
It
Is
does.
there some kind of organizational system?
The kernel relies on sophisticated data structures. You can think of them as intricate spreadsheets and to-do lists
Mhm.
to keep track of all the memory allocations. It uses lists to track free and used memory blocks, tables to map virtual addresses to physical ones, and various other structures to manage memory efficiently.
So there's a lot of bookkeeping going on behind the scenes.
A lot.
But security's got to be a major concern as well, right? You don't want unauthorized programs messing with your computer's memory.
That's right. Memory protection is a fundamental function of the kernel,
Okay.
especially in multi-user systems like servers where many users share the same resources. It's super important to prevent one user's actions from affecting others
Right.
or compromising the system.
So how does the kernel act as this kind of security guard for the memory?
Think of it like a library with different sections.
Okay.
Some areas are open to the public, others are restricted to staff or specific researchers.
Okay.
The kernel works in a similar way, designating different parts of the memory for different purposes,
Ah.
creating boundaries between user programs and the core operating system, ensuring that no one can access restricted areas.
Okay, so it's all about creating these secure compartments within the memory. But what happens when a program needs more memory than is actually available?
Right.
Do we just hit a wall?
That's where a clever trick called virtual memory comes into play.
Virtual memory. What's that?
It's a technique that allows your computer to run programs and handle data that's larger than the actual physical RAM.
Wait, so it's like making something appear out of thin air.
In a sense, yeah. Imagine you're working on a massive jigsaw puzzle, but your table is too small to lay out all the pieces at once. Virtual memory is like having an extra table in another room.
Okay.
You keep the pieces you're actively working with on your main table, and when you need others, you fetch them from that extra table.
So the kernel's essentially juggling pieces of the puzzle between these different tables.
Exactly. It uses a combination of RAM and a portion of your hard drive called swap space to create the illusion of more memory.
Wow.
It keeps track of which parts of the program's data are actively being used, stores that in RAM, and less frequently used data is swapped out to the hard drive.
That's incredibly clever. But I imagine moving data back and forth between RAM and the hard drive takes time.
It does.
Isn't that slower than just accessing everything from RAM?
Yes, accessing data from the hard drive is inherently slower than from RAM. However, virtual memory allows your computer to run programs that would otherwise be impossible. It's a trade-off.
Right, between capacity and speed.
Exactly.
So it's about making the best use of limited resources.
Right.
But there must be ways to speed things up. I mean, waiting for data to be swapped in and out all the time, that would make the computer feel really slow.
You're right, and that's where cache comes in.
I've heard of cache. It's like
Yeah.
a speed boost for your computer, right?
Exactly. Cache is smaller, much faster type of memory that stores frequently accessed data. Think of it like keeping your most used cooking utensils within easy reach on the counter,
Okay.
instead of having to dig through drawers every time you need them.
So the kernel strategically places certain data in this fast lane to improve performance.
That's right. The kernel manages the cache, deciding what data gets stored there and when to update it based on usage patterns.
Okay.
By keeping frequently accessed data in cache, it can significantly reduce the need to access that slower main memory or even the hard drive.
Okay. I'm starting to see how all these pieces fit together. So the kernel is acting like a master coordinator,
Mhm.
managing memory allocations,
Right.
ensuring security,
Uh-huh.
and optimizing performance.
And we've only just scratched the surface.
I can tell. This is already getting really interesting.
We haven't even delved into the specific techniques the kernel uses to manage memory, like the buddy system and slab allocation.
Ooh.
These are some of the clever strategies that ensure memory is used efficiently.
Well, I can't wait to learn more about those. But I think we need to pause here for now.
Okay.
We've covered a lot of ground already
We
in
have.
this first part of our deep dive.
So far, we've established that the kernel isn't just some abstract concept, but a vital component that manages these memory resources, provides security, and even creates the illusion of more space through virtual memory.
You've given us a lot to think about. But don't go anywhere just yet. In part 2, we'll continue our exploration of the kernel's memory management techniques, taking a closer look at how these systems work in practice.
Welcome back to our deep dive.
I'm ready to go deeper. Last time we talked about how the kernel acts as this master conductor, coordinating all the different aspects of memory.
Yes.
Now I'm curious to learn more about those specific memory management techniques you mentioned.
Okay.
The buddy system and slab allocation. These sound like they play a crucial role in keeping things organized and efficient.
They do. They absolutely do. Let's start with the buddy system. This is a clever algorithm for managing blocks of memory.
Right.
Imagine you have a large cake.
Okay.
That needs to be divided into pieces to share with your friends. You could cut it haphazardly, ending up with pieces of all different shapes and sizes. Or you could use a more systematic approach, dividing the cake into halves, then quarters, then eighths, and so on.
Okay, so the buddy system is all about creating these neatly divided portions of memory.
Precisely. It divides the available memory into blocks, always using powers of 2, 2, 4, 8, 16, and so on. When a program requests memory, the kernel finds the smallest block that can accommodate the request.
Gotcha.
If a larger block is needed, it keeps splitting larger blocks in half until it finds a perfect fit.
That sounds like a really organized way to allocate memory. But what happens when a program is finished using a block? Does the kernel just leave it empty?
No, that would lead to wasted space. When a block is freed, the kernel checks if its buddy, the adjacent block of the same size, is also free. If it is, it merges them back together, creating a larger block available for future allocations.
So it's like putting the cake pieces back together to form a whole cake again.
Exactly.
But why is this merging process so important?
It helps prevent a problem called fragmentation. Imagine if you kept cutting the cake into smaller and smaller pieces without ever merging them back together.
Right.
Eventually, you might have a lot of tiny scattered pieces, but no single piece large enough to satisfy a new request.
Okay, so fragmentation is like having a lot of small, unusable pockets of memory scattered throughout, even though there might be enough total free space to satisfy a request.
Exactly. The buddy system helps mitigate this issue by intelligently merging those free blocks, ensuring that there are larger contiguous chunks available when needed.
That makes a lot of sense. Now, what about slab allocation? You mentioned that earlier as well.
Slab allocation, it's another technique the kernel uses, and it's specifically designed to handle the allocation of small objects efficiently. Think of it like this. You're preparing a large batch of cookies,
Okay.
and you have a set of standardized cookie cutters. Instead of molding each cookie individually by hand, which would be time-consuming, you use the cookie cutters to create uniform shapes quickly.
So the kernel is using these cookie cutters to create pre-sized chunks of memory.
Yes, these cookie cutters are called caches,
Okay.
and they hold pre-allocated objects of specific sizes. The kernel can then quickly grab one of these pre-made objects when needed, instead of having to go through the more complex process of finding and configuring a new memory block each time.
That sounds incredibly efficient.
Hmm.
But what kind of objects are we talking about here? What sort of things are being pre-allocated in these caches?
Kernel objects are essentially data structures that the kernel uses to manage various aspects of the system.
Okay.
These can include things like process descriptors, file system nodes, network buffers, and many others.
So it's like having a pre-stocked toolbox with all the essential tools readily available for the kernel to use.
Precisely. Slab allocation reduces the overhead associated with repeatedly allocating and deallocating these small objects, leading to significant performance gains.
Wow. I'm really starting to appreciate the level of thought and complexity that goes into managing memory efficiently. It's a lot more than just handing out chunks of RAM.
It is. It
Okay.
certainly is. And we haven't even talked about the different types of memory involved.
Okay.
So far, we've been focusing on main memory, or RAM, which is the primary storage location for data and instructions that are actively being used.
Right.
But there's another key player in this memory management game, secondary storage.
Right. We briefly touched on this earlier.
Right.
Secondary storage is like the long-term memory of the computer, right?
Exactly, secondary storage, which includes devices like hard drives and solid-state drives, is where data is kept when it's not actively being used. It's like a vast library or archive holding everything from your operating system files and applications to your personal documents, photos, and music.
So main memory is like the active workspace, where things are happening in real time. And secondary storage is like the filing cabinet, where things are stored for later retrieval.
That's a great way to put it. And the kernel plays a crucial role in managing the flow of data between these two areas.
Okay, I'm curious about how that works. How does the kernel decide what data to keep in main memory and what to send to secondary storage?
It's a complex process, but essentially the kernel tries to keep the most frequently accessed data in main memory for quick access.
Okay.
When a program needs data that's not currently in RAM, the kernel retrieves it from secondary storage and loads it into memory. Conversely, when data is no longer actively being used, the kernel might swap it out to secondary storage to free up space in RAM.
So it's like a constant dance between these two types of memory,
Yeah.
with the kernel acting as the choreographer.
Exactly. And this dance is intricately linked to the concept of virtual memory that we discussed earlier. Remember how virtual memory allows your computer to run programs and handle data that's larger than the physical RAM you have?
Yes, it's like having that extra table for puzzle pieces.
Well, that extra table is essentially your secondary storage. The kernel uses it to store portions of programs and data that aren't immediately needed, freeing up space in RAM for more active processes.
So it's all about creating the illusion of more memory by cleverly managing the flow of data between RAM and secondary storage. But this swapping process must have a performance impact, right? I mean, accessing data from a hard drive is much slower than from RAM.
You're right, excessive swapping can lead to a phenomenon called thrashing, where the system spends more time moving data back and forth than actually processing it.
Oh, wow.
This can make the computer feel sluggish and unresponsive.
So it's like a traffic jam in the memory lanes. Is there anything that can be done to prevent this?
Yes, there are several things that can help. One is to simply have enough physical RAM to accommodate your typical workload. The more RAM you have, the less the kernel needs to rely on swapping.
Makes sense. So upgrading your RAM can be a good investment if you're experiencing slowdowns.
Absolutely. Another important factor is being mindful of how many programs you have running simultaneously. Each open program consumes a certain amount of memory.
Right.
So closing unnecessary applications can free up resources and reduce the need for swapping.
So it's not just about the physical hardware, but also about how we use our computers.
Exactly. And there are other things the kernel can do to optimize memory usage, like compressing data in RAM or using more sophisticated algorithms to predict which data is most likely to be needed next.
This is all incredibly fascinating, but I have to admit, it's a lot to take in. It seems like the kernel is constantly juggling multiple tasks, allocating and deallocating memory, managing different types of storage, and optimizing performance.
It's a complex and demanding job, but the kernel handles it with remarkable efficiency.
Right.
And we haven't even touched on more advanced techniques like memory mapping.
Memory mapping, what's that all about?
It's a powerful technique that allows the kernel to directly map files from secondary storage into a process's address space, making it appear as if the entire file is loaded into memory, even though only the parts currently being used are physically loaded.
So it's another way of creating the illusion of more memory.
In a sense, yes, but it's more about efficiency than illusion. Think of it like reading a large book. You don't need to have the entire book open in front of you at all times.
Yeah.
You only need to see the pages you're currently reading.
So the kernel is essentially creating these virtual pages for files, allowing programs to access only the sections they need without having to load the entire file into RAM.
Exactly. And this technique has several advantages. First, it reduces the amount of physical memory needed, as only the actively used portions of the file are loaded. Second, it can improve performance by reducing the need for repeated read and write operations.
That sounds like a win-win situation.
Yeah.
But how does the kernel know which parts of the file to load and when?
It uses a technique called demand paging.
Okay.
Essentially, the kernel only loads pages from the file into memory when they are actually requested by the program.
Oh.
If a page is not being used, it can be swapped out to secondary storage to make room for other data.
So it's like a just-in-time delivery system for file data. Only the necessary pages are loaded when they're needed, optimizing memory usage and performance.
Precisely. Memory mapping is a powerful tool that the kernel uses to manage large files efficiently, especially in applications that work with massive datasets, like databases or video editing software.
This is all incredibly insightful. I'm starting to see how all these different techniques work together to create a highly efficient and flexible memory management system.
And we've only just begun to explore the depths of this fascinating world.
I can tell. But I think this is a good point to pause and reflect on what we've learned so far. We've covered a lot of ground, from the buddy system and slab allocation to the interplay between main memory and secondary storage, and the clever tricks of virtual memory and memory mapping.
Indeed. And in our final segment, we'll explore some of the broader implications of the kernel's role in memory management, including its impact on system security and performance, and perhaps even ponder some thought-provoking questions about the future of computing.
Sounds intriguing. I'm eager to hear more. We'll be right back after a short break. Welcome back. We've been on quite a journey through the world of kernels and memory.
Yeah.
It's amazing to think that all this intricate activity is happening right now inside our computers, without us even realizing it.
Right.
As we've seen, the kernel plays a really crucial role in keeping everything running smoothly and efficiently.
Absolutely.
It also makes you wonder, what happens if something goes wrong?
Yeah.
I mean, we've talked about how the kernel is responsible for security,
Yeah.
preventing unauthorized access to memory.
Right.
What if there's a vulnerability or a bug in the kernel itself?
Right.
Could that open the door for, malicious actors to wreak havoc?
That's a really important point. The kernel, because it has such privileged access to the system's core functions, is a prime target for attackers. If its security is compromised, it's like handing over the keys to the kingdom.
Wow.
An attacker could potentially gain control of the entire system, stealing data, corrupting files, or even bringing down critical services.
So it's essential that the kernel is as secure as a fortress.
Absolutely.
How do developers ensure that? I mean, no software is perfect, right?
Right. No software is immune to bugs, but kernel developers take security extremely seriously. They use rigorous testing methods, code reviews, and security audits to try and identify and fix vulnerabilities before they can be exploited. And when vulnerabilities are discovered, they're usually patched very quickly.
So it's constant kind of cat and mouse game between the developers and those who seek to exploit weaknesses.
It is.
But what about those unintentional errors we talked about earlier? Could a simple kernel bug lead to problems like memory leaks or system crashes?
Absolutely. Even seemingly minor errors in the kernel code can have cascading effects. A memory leak, for instance, might not be immediately noticeable,
Right.
but over time it can gradually deplete the available memory, leading to performance degradation and eventually causing the system to become unstable or even crash.
It's like a slow drip from a leaky faucet,
Exactly.
gradually filling up a bucket until it overflows.
Yeah, and then there are errors that can cause more immediate and severe problems like data corruption or sudden system crashes.
Right.
That's why it's so important to keep your operating system updated. Kernel updates often include critical bug fixes and security patches that help protect your system from these sorts of issues.
This is all really insightful, and it makes you appreciate the kind of delicate balance that's required to keep a computer running smoothly.
Yeah.
But looking ahead, I'm curious about the future of kernel memory management.
Okay.
With all the advancements in hardware, things like non-volatile memory, faster processing speeds,
Right.
will the kernel even need to manage memory in the same way it does today?
That's a great question. New hardware technologies are certainly pushing the boundaries of what's possible. Non-volatile memory, for example, which can retain data even when the power is off, has the potential to blur the lines between RAM and storage, leading to new memory architectures and management paradigms.
So it's like having the best of both worlds.
Right.
Speed of RAM combined with the persistence of storage.
Exactly. And with the rise of parallel processing and multi-core systems, the kernel's role is becoming even more complex. It needs to efficiently manage memory access across multiple processors and ensure that data is synchronized
Yeah.
and consistent.
It sounds like the kernel is evolving into a much more sophisticated conductor,
It is.
orchestrating this whole symphony of hardware resources.
That's a great way to put it. And as these technologies continue to advance, we can expect to see even more innovative approaches to memory management, perhaps even leading to systems where memory management becomes almost invisible to the user.
Well, I think we've reached the end of our deep dive, and it's been an incredible journey. We started by unpacking that fundamental role of the kernel as this memory manager, explored the complexities of different techniques like the buddy system, slab allocation, virtual memory, and memory mapping. And we even touched on the future of memory management in light of these evolving hardwares.
Yes.
It's been a pleasure exploring these concepts with you.
Likewise.
And I hope this deep dive has given you, the listener, a greater appreciation for the intricate workings of kernels and memory management. I know I'll never look at my computer the same way again.
And remember, even though the kernel operates silently behind the scenes, it's really the unsung hero that makes all of our computing experiences possible.
Absolutely. So next time you open an app, stream a movie, or even just save a file, take a moment to acknowledge the incredible work of the kernel and its masterful management of memory. Until next time, keep diving.